In this last section, we're going to be talking about interference and the Doppler effect. And let's start with the Doppler effect. You'll recall that I said that the Doppler effect is the effect of the motion of either the source or the object, receiver, or both on the velocity of sound. So we'll be doing some calculations based on changes in velocity that are caused by motion of the source or the observer. The first problem: what frequency is received by a person watching an incoming ambulance moving 100 kilometers per hour and emitting a steady 800 hertz sound from the siren? And so basically, in this problem, you have an individual who's sitting there, and the ambulance is coming in their direction at 100 kilometers per hour, and it's emitting a sound, and so at 800 hertz. And what it wants to know is, what does this person actually hear? And the formula you need for this is the observed. Now, this is the formula when there's no motion for the observer. So the observed is equal to the actual source frequency times a correction factor for the motion. And that correction factor is the velocity of sound divided by the velocity of sound plus or minus the velocity of the source. Now, how do you know which velocity to use? If the object is moving toward, it's going to increase the velocity. Therefore, you'll use a minus sign because this is in the denominator. Conversely, if the source is moving away, it's going to decrease the frequency. Therefore, you use a plus because you want a bigger denominator. So in this case, you put 800 in times, now the velocity of sound here is given at 345 meters per second. And you're going to subtract the velocity of the siren. Now, it's 100 kilometers per hour, and there are 1,000 meters in a kilometer and 3,600 seconds in an hour. If you do the math here, you get 30.6 meters per second, and that's what you put in here. And then if you do that math, then the observer hears a frequency of 878 hertz instead of 800, and that's the Doppler effect. Now, B basically states that once the ambulance passes the person, so now they're moving away. The calculation is exactly the same, except because it's now moving away from the observer, instead of subtracting the speed, you add it, so that this denominator is bigger and makes this number smaller. And therefore, you add 30.6 to that. You do that calculation, and you get 735 hertz. Number 32. Number 32 is exactly the same. What frequency is received by a mouse just before being dispatched by a hawk flying at 25 meters per second and emitting a screech at 3,500 hertz? The speed of sound is 331. It's exactly the same formula and the hawk is moving toward the mouse, and so you'll be subtracting that. So you'll take the 3,500, which is the frequency of the screech, times 331, which is the velocity of sound they give you, divided by 331, and in this case, minus the 25 meters per second the hawk is traveling. And that means that this mouse actually hears 3780 hertz instead of 3500. Number 34. Now, number 34 states that you have a commuter train that blows a 200 hertz horn as it approaches a crossing. The speed of sound is 335. An observer waiting at the crossing receives a frequency of 208. What is the speed of the train? Okay, so it's the same formula. So the frequency of the observer is equal to the frequency of the source times VW over VW. Now the frequency of the observer is greater, and so that means that this must have been subtracted. Okay, so Fs is 200, F observed is 208, so that means that this, whatever the train is doing, in this case, this is source actually, has to be subtracted. Okay, so we put numbers in here. There's 208 is equal to 200, and the speed of sound in this case was 335. 335 minus V source. Okay, so now all you have to do is solve this, and V source is going to come out to be 12.9 meters per second. Now the second part of this problem says, what frequency does the observer receive as the train moves away? Okay, so it's now that you have this, they want to know what the frequency of the observer is as the train moves away. So you have 200 times 335 over 335. It's moving away, so plus 12.9. And that's going to equal 193 hertz. And it should be, this is 208, so it's about 8 different. It should be pretty close to that. It actually came out to 192 and change. So this difference, the fact that this isn't 192, is because of rounding in the calculations. Number 35. Can you perceive the shift in frequency produced when you pull a tuning fork towards you at 10 meters per second on a day when the speed of sound is 344? You calculate the change in the frequency and see if it's greater than 0.3%, because you can detect a 0.3% change in frequency. Okay, so 35 says, V observed is equal to V source, or frequency of source, times VW over VW, and in this case it's coming towards you, so minus VS. So that's going to be, and the you don't know the tuning fork or so the question is F observed over Fs, is that going to be greater than 0.3%? So 1.003. So if you put 300 and then 344 plus 10 is 354, or minus 10, 334. What's that number going to be? And that number is actually 1.03. So it actually changes the frequency by 3%, and therefore you can hear the difference because you can detect 10 times that much. number 36. And number 36 is a little more challenging because you have both the observers and the sources, because there are two birds flying at each other like this. And we'll call this is bird 1 and this is bird 2. And so you have to do the calculation from each perspective. So for example, if the bird 2 is the observer, so the observer bird is bird 2, and that means that bird 1 is the source. And that's going to be, first of all, the moving source is VW over VW minus the velocity of the first bird. But that's also multiplied because the observer, and so you just have to keep these straight. So now this is source 1 because we're doing observer 2, right? Source 1's moving toward, and so that's going to equal 3,200 times the speed, which is the speed of sound, which is 330, over 330 minus 15, because that's the velocity of that first source. If you do that calculation, you get 3580 for that bird. The second bird, actually the first bird, so is the source of the second, and that's going to be the same 300, or let's just skip this and say the second screech is 3,800 times 330 over 330 minus 20, which is going to equal 4,230. We have one more set to do, and it has to do with the sound over an open tube, and I'm just going to continue with this tape, even though it's going to run a little bit long. Number 39. What beat frequency would be present if the musical notes of an A and a C are played together? The two frequencies are given. A D and an F with the two frequencies, and then an all four. Remember the beat frequency. The beat frequency is equal to F is equal to the absolute value of one minus the other. So and it's the absolute value, not parenthesis side. So in the first case, it's going to be 264 minus 220, which is 44 hertz. In the second case, it's going to be 352 minus 297. So that's going to be 55 hertz. If you play them all together, then you get all the combinations. And the various combinations include 352, include the two I've already written, plus 352 minus 220, 352 minus 264, 297 minus 220, and 297 minus 264. So this is 132, 88, 77, and 33. Now, that's why when all these notes are played together, you don't hear it, because these are all jumbled together in such a way that you can't hear the various beat frequencies. 41 states that a tuner plays two notes, plays his tuning fork and the piano tune, and he hears a beat every 2 seconds. A beat every 2 seconds is a period of 2 seconds, which means the beat frequency is 1 over the period, which is 0.5 hertz. And that means the frequency of the string is either 264, and it's either plus or minus 0.5. Number 44 gets into that last section I was talking about in part 1, which is a note played over an open tube, opened at both ends. Now, it tells you the fundamental, in this case, is 90. So that means that the first is equal to n over the velocity of sound times 2L. Now, that means you know that 90 is equal to 1 times the velocity of sound. If the velocity of sound remains constant and you put a 2 in here, then this 2 cancels this 2, so the next fundamental is going to be 2 times this. And so it's going to be 180 hertz. And if you put 3 in, you're going to get 3 times that, or 270. If you put 4 in, so this is the third fundamental, you get 4 times 90, or 360 hertz. So those are the 3 overtones. Now, as it says in the book, it's more complicated than that because of the split reed. I don't know much about musical instruments, but there you go. What is the length of a tube that has a fundamental frequency of 176 and a first overtone of 352? The speed of sound is 343. Okay, so the speed of sound is 343. And you know the fundamental is 172. And so the fundamental is equal to n VW over 2L. Well, n's equal to 1, so you can cancel that out. So you know that 172 is equal to 343 over 2 times the length. And if you solve this for the length, you're going to get 0.97 meters. So that's the length of that tube. The last problem, problem number 49. By what fraction of the frequencies produced by a wind instrument change if the temperature changes from 10 to 30 degrees? This is why this question gets to a problem that occurs when you're playing music outside, because the temperature does affect. So you have 2 velocities. You have V1 and V2, and those 2 velocities are affected by the temperature. 331, 331. The first is going to be it was 10 degrees, so 283 over 273. And the second is 303 over 273. Now, once you do all this, the frequency changes because frequency is directly related to the velocity. Is going to be the velocities And so at a higher, I mean, you can do it either way. Let's do it this way. And so that's going to be 349, which is this calculation here, divided by 337. And that means it's 1.04. 1.04 means the change in the frequencies is 4%, which is why when somebody, if they tune their instrument inside and they go outside and the temperature is meaningfully different, they have to retune their instrument. And that ends the homework for this week.